Okay, so before we start, any questions for the project and also the like the exams? I'm still grading the exam, and hopefully I could release the grades by next week. And since we have fall break for Monday and Tuesday next week, right? So probably after the fall break, you will have the grade released as well as the homework to grade release. Any questions so far?
Yeah, when do we come to pick up the RC car kits?
Yeah, that's
When do we
good.
get those?
Yeah, that's a good question. So I have asked the secretary of the department to put the order, since I have to know how many groups there are, and so that is done last Thursday, and hopefully around 1 week, you should be able to get the car, because yeah, basically it's on Amazon, so it takes like 1 week also. So probably next week when you come back from the fall break, there will be the kit. Basically, you need to disassemble it. It's a whole RC car, right? You need to disassemble it and take the part you need. Mhm.
Okay, and to sign up for groups, do we have to like send you an email or something?
Yes, I think that's that is sent through an email. This requirement. Oh, I didn't realize you haven't found a group. I think you need to let me
No,
know.
it's just you hadn't told us to email you lists of group members.
Oh, I thought I have reached you through the email. Let me double check.
I think you did send out an email.
Yeah, yes, that's
If there was an email, I don't remember getting it. So
yeah, yeah, that's a email through the micro system to everybody. So yeah, just yeah, you can let me know as soon as you can, such that I could add on another purchase if you have another group. If you join one group, there's no need to make another purchase. But if you have a different group, just let me know.
Is there a way to see where the current groups are?
Yeah, I can release that, no problem. I can release that information on my courses.
Okay.
Okay, anything else? Okay.
This might be a little off topic, but is there homework 3 coming up?
Yes, that's what I'm about to tell you. So there's a homework 3 after this lecture, because the questions requires the content taught in this lecture. And since you have a fall break, we usually have the due on Thursday. So I will switch it to Wednesday, right? So you have 1 more days after the break. But there is a homework. Okay. Anything else?
Since we're on the topic, so fall break is Monday, Tuesday. We're not gonna have class on that Monday. I'm guessing we're gonna have lab on that month. We're gonna have lab on that. I have lab on Friday, so I still have lab that week.
I guess so, but I need to confirm with the TAs. But you since since the lab starts on Wednesday, and so I don't think they will be affected by
Okay, yeah.
by the break. All right, are we good? Okay, good. Let me share my screen. So we talk about some of the fundamental chemistry beneath the photopolymerization process, right? So what essentially happens during the process is the polymer become cross-linked after the light applied to the resin during the process. And that's a unique property. Basically, the thermoplastic are not cross-linked. So the material used in thermoplastic, I mean, the thermoplastic material cannot be used in this process. As I mentioned, this cross-link happens during the process, and there has to be a light source. So that is very important to look at this photocuring reaction. And basically, that is the process of hardening a liquid resin through the laser or other light source selectively applied to the resin. And there are a few parameters that need to be considered. First is the penetration depths. Basically, that is the depths beneath the liquid surface at which the energy intensity has been reduced to approximately 1/3. Actually, it's 1 over exponential number. I mean, Euler number, 1 over E. That's the penetration depth. Here, you can roughly use 3 here. Basically, the Euler number is 2.7 something. So here I just put 1 over 3 here. But you should be knowing actually it's the Euler number, 1 over E. Right? And another parameter is the scan velocity. Basically, that's the speed at which the laser beam is scanned over the liquid resin, and that is controlled by the machine or by you, right? Basically, you can control how fast or how slow the laser scans. Another parameter is this critical exposure. That is the energy per unit area need to produce the gelation of the photopolymer. So basically, if the energy per unit is below this critical exposure, the liquid material will not be solidified, will not be starting to solidify. So that's the what this means, right? Basically, that's a I would say starting point for this gelation happens. The last one is the cure depth. So that is a function of the penetration depth, critical exposure, energy intensity, exposed area, and the exposure time. So basically this let me find a notation. So this cure depth is the is what we are looking at. So basically that will tells you what is the width of the laser trace, and that is a function of all these parameters, and this is usually what we are looking at for solving some problems. As you can see here, this penetration depth and also the critical exposures are the property related to the material. And the scan velocity is a variable controlled by the process or by who designed the machine, designed the process. So we can play with these parameters and have a computed cured depth for certain materials and light source with certain energy source applied. So let's take a close look at it. So we need to, all right, now we have this equation here, and basically PL is the laser power, and W0 is this Gaussian half width of the beam. So as you can see here, that represents the beam radius, right? And this EYZ is the laser exposure. Basically, its unit is millijoule per centimeter or some other equivalent unit. But overall, it's the laser exposure. And this laser exposure is the function of the depth beneath the surface of the horizon and the distance from the center of the beam. As you can see here, this can be considered as the center of beam, and you will have a different energy at all these points, right? And also, it depends on how close this point is. Is from the surface of the horizon. And another parameter in this equation is the velocity of the beam, Vs. So you can see here, it is placed over here, and the penetration depth dp, which is put here. As I mentioned, dp is the depth at which the energy is 1/e, that of the energy at the surface. So basically, the energy will become lower and lower sorry, with the distance increase from the surface. So if the depth, the penetration, if the energy becomes 1/e, and that will be the penetration depth we use here. So basically, we need to use this equation to do some computation. And from here, you can tell, let me go. All right. So from here, you can tell the parameters are the laser, the parameters which are related to the laser or laser scan system. As I mentioned, the power of the laser, that is, you can control it by changing the laser or the laser scan system. And another thing is the velocity of the beam. That is what you can control. And some other parameters related to the horizon you choose, the depths, the penetration depths, right? dp is related to the horizon. For different material, different horizon, that could be different penetration depths. So intuitively, if we increase the velocity, scanning velocity, what happens to this equation? So let's see, we have everything remains the same, but only increase the velocity of the scanning, Vs. So it turns out if everything is the same, but this got increased, then you will have the whole term become smaller. And then you have your energy intensity, laser intensity becomes smaller. So that's how it affects the this. So you can just imagine if you have a system, right? And you just use you just let the laser beam scan on this horizon, and if you use very fast speed to move your laser, that means a high Vs. So it turns out many of the horizon will not be cured, right? And that's how you think of the effect of Vs increasing. So that means you have to have a proper Vs during the process in order to cure the horizon. And all right. So another interesting question is the something like this. If we have all those parameters given, and there's a question asking you what is the laser exposure, which is the EYZ, right? at a depth of 0.05 millimeter and a lateral distance 0.03 millimeter from the center of the beam. That means if you have the figure, that is the distance from that point to this vertical axis, right? And with all this, how you compute this laser exposure. So what you want to do is just first have the equation and plug all these known variables, and then you should be able to find the laser exposure. For example, for this one, you have the laser power, right? That's where the laser power placed, right? And also the W0, VS, and also DP. I think DP is something here, right? And so on. And it turns out you can compute the number like this. Basically, it's simply substitute the known parameters to the equation, and then you should be able to find out those numbers. Mm-hmm. Another interesting point is this. Basically, you want to look at this figure. So there will be some overlap of the different. Yeah, go ahead.
I have a question.
Yeah.
In the case of the supports, supposedly I understand. No? I don't know if it's correct.
Yeah.
You can correct me. Can that energy intensity be manipulated? For example, if I need that my supports, I don't need that my supports needs to cure a lot, but my solid part, yes. So that's the intention for this equation, or not?
Well, I think that's a good question. I don't know whether those providers of the printers manipulate the power, but that's possible. But one thing you want to be aware of is you are still, the support will do the job. That means we'll support the main part, and that will be a load applied to the support. If this curing is I would say weaker than the one for the main part, whether this could bear the same amount of load without collapse, that will be the essential question you want to look at. Probably, I think they will not afford this. They will not get a risk of it. So instead, they just have the same intensity. I mean, energy, laser intensity, and cure it as strong as the part. I think that's my guess. I didn't check it, but that's interesting to look at.
Okay.
Basically, you are suggesting some support material which is easier to be removed, right, compared to what we have right now. And that could be a very interesting direction.
Yeah, because we have a point, a specific point, so we can manipulate that in this point for the support, you can't cure for a lot of energy, but for the solid part, you can. So
right.
Yeah.
Yeah. I think that's that you can also check the have some search on the literature, but I didn't see some related work. And yeah, you can figure out yourself if it is feasible. The only thing is the feasibility, whether it still is still good enough to support the main part for less energy exposed. Right.
Thank you, just curiosity.
Yeah, no problem. Yeah, and let's move on. So basically, there for each of the trees, scan trees, and there's a so-called scan pitch, which is the step over a distance between the adjacent laser track when the laser scans the resin to fill the area of a layer. And as you can see here, usually it's desired to have little overlap for each of the laser track or each of the scan trees, such that there will be a more compact region instead of having large area of void space. You can see here there's still some empty space, but if you decrease the distance between the track, this area can be decreased. I mean, this space can be decreased. Another one is the overlap between each of layer, right? As you can see here, you have n-1 layer, n-1th layer, and nth layer. And whether you want to have some overlap between the two layers, right? That is also another question. Basically, there are multiple solutions, different strategies for such a pitch in both layer-wise and also the track-wise planning, and that basically you need to control the path of the scanned laser as well as the energy intensity. Yeah. Another question is, again, the critical exposure. So as I mentioned, basically this critical exposure indicates if a critical energy level, if the energy does not exceed or is less than the EC, then there's no curing happen. So you have to make sure the energy intensity will be larger than EC, and that will determine the curing. That will determine when there will be a curing.
Professor,
Also, yeah,
could you erase all the other lines that are on the thing?
sure. Let me do it.
Thank you.
Yeah. I think there are some ones from the PowerPoint. Let me use the PowerPoint tools. Oh, it cannot be erased. Okay, I think I have another file. During the break, I will find another file without all this annotation. All right.
Okay, yeah, no
Yeah,
problem.
now we can just having this, right? It's
Okay.
to save a little time. Okay. Yeah, I mean, in that case, if you know the critical exposure here, then you could determine the width of the cured line at the surface. If we look at the figure, that means, wow, that's really, let's find a good one without too much annotated. Yeah, so basically, if you know what is the critical exposure, you can tell what is the width of the cured region at the surface. So that could be computed. All right, let's move on. Basically, there are some special numbers you want to keep in mind. One is the maximum cure depth, and that happens when when you talk about the surface of the resin. And in this figure, basically, it talks about this no, it talks about this number. Basically, that's the maximum depth this laser could cure in the Ryzen. And basically, you can utilize this equation. And what is missing here is this Emax, right? That is the maximum exposure energy. So as we know, the laser energy will reach its maximum if you are talking about at the surface. Also, even at the surface, if it is closer to this 0 point, this horizontal, the central point, the energy will become larger. That in that case, the maximum exposure energy Emax will happen at this 0 point. So you can substitute 0 in this equation and have the Emax like this, and substitute the Emax here, then you will have the maximum cure depth, which is this one. Another computation you want to keep in mind is, what if you know a desired cure depth? I mean, that's possible. When you plan a process, right? You could have some desired cure depth. And the question is how you realize it with given laser energy and material, right? The only thing you can control is the velocity, laser velocity, VS. And basically, you can substitute all the known numbers into this again and figure out what will be this VS by using this equation. All right. So some of the computation will be relevant to these equations. So be aware to these pages. Oh, I just realized there are too many annotations left from last class, but it cannot be removed. Sorry about that, but I will find a new one without anything added for you. All right. Yeah. So another problem is also the distortions introduced in the process. And there are still curling happens. For example, like the one showing here, if you have a large flat horizontal surface, and there will be a significant curling during the process. That is again because of the shrinkage. There will be shrinkage during the solidification of the material, similar to the fused deposition modeling process, but it has different costs, right? For the fused deposition modeling, that is because a thermal shrinkage, but here there's a different fundamental mechanisms for the solidification of the material, but still there will be a shrinkage. And that will cause the curring because of the different shrinkage ratio of the two different layers. Then the problem, the way to kind of remove such effect is to first you could do something to your material, right? To play with the different combinations of polymers and also the other photo curing materials. And another possibility is to play with the orientation, since it will, the most serious kind of curing, curring happens for those a large flat horizontal surface. If you change the orientation, right? That could be make the original horizontal surface become a vertical, right? If you rotate it by 90 degrees, that could be one solution. For example, for this case, you can just flip it to the by 90 degrees in the counterclockwise direction. Then there's no such a big flat horizontal surface. Such kind of curving could be removed, and also you could change your design a little bit to prevent design such kind of features, you know, on the geometry of your part. So all these are possible solutions for preventing the curving of your prints. So for the printed parts, again, there are post-processings which could introduce other appearance and functions to the printed part. For example, like the electroplating process. Basically, you could basically add on a thin layer of metal onto the polymer parts right after the process. Here shows some examples, and basically that will serve for certain functions in certain applications, right? I would like to skip this maybe. Basically, that's the steps for the plating of the plastic, and for many of those electroplating, what you want to do is to charge your plastic part and make it available for the metal particles with the electro charges applied, and then you can start with other steps to do plating. So okay, another interesting application is this Invisalign. I think I introduced this in the beginning of the class, and it is I would say a very successful business based on the this stereolithography process, and the key here is to create a series of teeth between the original teeth of the patients and the patient's desired teeth, and there are transitions in between of the two, usually 12 to 48 aligners, and each of the aligner is worn for about 6 weeks, and all these aligners need to be fabricated first by a 3D printing to print model of the teeth, and then a thermoforming to generate this aligner based on the printed teeth, right? And the material is the polycarbonate or polyurethanes, and basically you want to have a very thin layers for this material, and at the same times its strength should be good enough for the purpose to align the teeth. And so keep it in mind, the final teeth aligner is not printed. This is not printed. Instead, the teeth is printed, and then there will be a thermoforming. Use the thin sheet to form such aligner, and That's how it works. So there used to be students asking, how could this kind of thin layer of teeth aligner to be fabricated using the 3D printing? Actually, that's a mistake. That's a confusion. Actually, it's the teeth to be 3D printed, and then the teeth will be used as the mold in the thermal folding, right? And that's the process of this.
But this polyurethane or polycarbonate is special, as Invisalign say in your page, in your website, or is a normal polyurethane sheet for thermoforming?
Yes, that's the normal the biograding sheet instead of there's no magic for this, I would say.
Okay.
Yeah,
It's because the doctor think yes,
Mhm.
that they were printed directly to the 3D printing
Mhm.
machine,
Mhm.
but yes, it's a mistake.
Yeah,
Okay.
yeah, I could show you. I will show you how it looked like. I know it's a little annoying to have all those annotation on, but yeah. Maybe I can, yeah, let me just copy the link out and open it in a different browser such that, just 1 second. Let me share this website instead, such that you will have no such a annoyed annotation.
The idea of mass customization is really basis of the company's existence. The idea that originally sparked the whole thing was, can we use digital technologies to kind of bring the science of teeth straightening into the next generation? When Invisalign started, 3D printing was primarily used for prototyping in a limited number of parts. So what we had to do is really figure out how to make that into a production process.
3D printing is really kind of the foundation of our manufacturing process. It's the starting point. When we make a mold for every stage of a patient's treatment, we use 3D printing to make those molds.
If you think about an injection molding type of process, where we're only producing the same type of part, millions of those, so that's been done before. Or you think about a very specialty 3D printing application, where each part is unique, but they're produced in a small quantity. What we've done at Align is really combine those two. We've treated almost 6 million patients, and the growth is actually accelerating. We produce about 320,000 parts every day.
From a support perspective, 3D Systems has been instrumental in helping us get to where we are today.
What makes Align's mass customization so unique is not only are we producing millions of parts every month, but each one of these parts that we produce is unique. And this is really the, as far as I know, the only true example of mass production using 3D printing.
To where we are.
Not only are we producing so unique is mass customization
Helping us has been
every day.
3D Systems to where we are
So unique is not only are we producing
today.
Align's mass customization unique. Not only are we producing every month, and this is unique. And this is really the, as far as I know, the only, and this is really unique. And the parts that we produce is unique.
I'm trying to find out where this to be thermal formed, but apparently it didn't show in the video. So y'all know what is thermal forming, right, or not?
Yes, of course.
Yes. How about others?
No, not really.
No. Okay. Let me show you the thermal forming. What thermal forming does, right? So such that you will understand what I'm talking about. Thermal forming, like.
But the problem is that the video is confusing because
Yeah.
they show,
Yeah, that's it. That's
the
the
marketing
problem.
strategy.
Yeah. that's why there are questions. Oh, you are actually let me see. Oh, it's a little. Let me instead of just finding the thermal the teeth application, just find some general ones. Okay, let's say this one. It's a little too long. See, this is the mode. This is the mode you used in the thermal forming, and this is the. Did I share the screen?
No.
No, sorry, I'm talking with the air. Okay, anyway. Okay, let me go back. See, this is the mode which is installed on the machine. As you can see here, this basically there are some patterns, right? Block pattern or pyramid patterns. And after this is installed, there will be the plastic sheet applied. See, this is the sheet used for the thermal forming. And what it does is, of course, there will be a heat up to make the plastic sheet softened. All right. And then another step is to see. Basically, the mold is moved towards the sheet, and there will be a vacuum machine to remove the air in between of the sheet and the form. And it turns out you will have the part created. So basically, if you talk about some of the plastic box for cookies, for you will always see in the grocery stores, that is made using such process. So you have the mold, you have the sheet, and through this process, you will have all the parts with the geometry created like this. See, right? So in the Invasor Align case, so what it prints is the teeth as the mold, and then the polycarbonate plastic sheet will be fabricated, will be applied to the mold, just like this, to create a thin sheet of the aligner. You got it now? So just remember, it's not directly printing the aligner. It's the printing of the teeth and then a thermal forming to create the aligner. All right. So let's finish this part. Let me share my screen. Oh shoot. It's not what I want. Yeah, that's what it is. Okay, there we go. So another application is the customized hearing aid. Basically, that's another example for the customized parts for each of the individual patients. So what it does is there will be a scanning of the patient's ear canal, and then the scanned 3D geometry will be used to create this kind of hearing aids, especially specifically the exterior parts of the hearing aids, and the electronics components will be inserted to such a experience for each of the individual patients. let's look at a video maybe. Just 1 second. Let me share it. Yeah.
2,000 square. Well, at Oticon, we've recently moved into a brand new 162,000 square foot facility. And the beauty is that we were able to do that and design it based on our 100 years of product design and manufacturing experience. So we were able to lay the facility out, taking advantage of that to optimize productivity and efficiency and really streamline the workflow. In addition to that, I think this expansion has allowed us growth for the future. So we were able to put the infrastructures in place to keep pace with the growing demand. It also enabled us to increase and upgrade all of our manufacturing equipment. And part of that manufacturing equipment consists of the SLA process. Now, for those that don't know what SLA is, it's called stereolithography apparatus. It's kind of a tongue twister. But what it means, it's really a great ability to take advantage of the new technology to create shells. We're able to double capacity and at the same time make a much more cosmetically attractive, smoother finish, comfortable fit product for the custom side of the business. Oticon produces a variety of BTE instruments and custom instruments to the marketplace. With the introduction of the Invisible in the Canal product Antigua, there is a growing custom product demand out there. With today's advances in technology, as well as the optimization in the design of making the product, we can make it smaller, comfortable fit, and the hearing care professional can fit a wide variety of hearing losses. And it goes beyond technology. Just because you have technology will not ensure you have a good performing product. It takes people. You know, and people are a key foundation within Oticon. So it's a combination of the technology and how to use it, using the people, using their understanding of what's important to make a good product. Put those two together. That's called success. I think it's important for the hearing care professional to understand, with this new technology, they still have a key role to play in the quality of the impression that they provide. And, you know, I'm often asked is, you know, what does it take in terms of an impression to make a good quality product? And it's really fairly simple. It's one of consistency. Is when an impression comes in, does it go beyond the second bend? Ideally, 2 millimeters beyond the second bend, full canal. Use that otoblock. I think that's important so that we can get a full, good size impression, including the concha, because the concha is also very important for a manufacturer because that's going to determine our locking points. Once we get that impression, the process we go through is we scan it. When I say scan, what we do is we make, through 2 cameras, we take what's called a digital point cloud. That's roughly 100,000 measurements in 2 to 3 minutes. So we create an exact replica of the impression that we get in. So after we do the scanning, we create a 3D image of that impression. Again, an exact replica. Now we print it. Now when we print it, we use the new technology. And again, that new technology makes it very consistent. We can have a very consistent product. So again, it's incumbent that we get a good quality impression. If we have that, it goes through the process of the shell making, it goes to our assembly floor, and then the technicians will take those components, put those components into the product for a product that's consistent, comfortable, as small a size as possible. So hopefully when you open that box, when you get that delivery, not only you're happy, but your patient will be happy as well. The question that comes up is what happens if we don't have a good impression? The hearing care professional might think with the advanced...
I think we can stop here, but that video presents how this kind of stereolithography process help the manufacturing of a hearing aids. All right, I think we can stop here. Let's have a 10 minutes break and let's go back at 10:10. All right. Okay, continue. So before we move to next process, let's look at some of the questions, which could be in your homework or the exam. Some example questions like this. So one question is related to the vector scan based stereolithography, and let's assume the laser scan has a VS millimeter per second velocity, and the QR trace has a WT width, and the layer thickness is LT millimeter. So how about we have we are requiring to cure this amount of volumes of the material, and also the overall part height is HM. Then let's estimate what will be the overall building time. Oh, by the way, there is a time TS required for each of the in between of each layers. So knowing all this, let's have an estimation of the overall time used for building the part. So I think I've talked about this a little bit during the class. So there are two set of time. One is the scanning time, right? Laser scan time. And another one is the time for spreading the resin, which is which this TS represents for the time spreading of the resin in between of the two layers. So and we need to compute the two set of time and put them together. So for the building time, right? What you want to do is first compute a volume scan rate by knowing this linear speed, the width of the trace, and also the layer thickness. So what essentially you have is, by multiplying the three together, you will have a volume scanning rate, which is in this unit. And then the time could be computed using this rate together with this overall volume, and that is how you have it. Then the spreading resin time for spreading the resin. What you want to do is you first have the layer numbers, because the overall height is H and the layer thickness is LT. Then H over LT, that's the layer numbers, right? And with this number together with the time for spreading the resin, TS, and you have all the time for building the whole part. I mean, all the time for spreading the resin for the whole part, right? That's what it is. And then you have the two and add them together. Now you have everything included for the overall time. So any question for this computation? Are you guys good? Okay. So another one, I think I also mentioned a little bit for during the lectures. I mean, the 2 weeks ago. That is the if you have the and the projection-based image for the projection-based process with the image resolution, and then you could decide what is the minimum 3D printed feature size. That is because in the projection, in the projection-based process, there are different angles for the projection, right? As you can see here, there is the angle along the x-axis and the angle along the y-axis. And also you have the image resolution. Then it's potentially you could compute what are the projected image, as long as you know the distance from the camera to the projected surface, right? Let's assume you have known this, which is in this case 40, right? If this is given and it is 40, then you could know what will be the projected image on the projection plane. In x direction, use some trigonometry. Since the angle is 26, and use the tangent function, right? Basically, this vertical line is 40 millimeter, and you want to know this, right? And this angle is 26 over 2, which is 13 degree, right? And then you can use the tangent 13 times this height, and then you will have the length, this length, and times 2, you will have the full dimension in the x direction. Basically, that's what this does. Same thing happens to y using this angle and use the using the distance. You will have what happens. What's the image size along the y direction? With this two, how you compute the actual feature size? So you have known the image resolution is this number, right? That means the projection after projection, the projected image will also be such a 1920 by 1080 kind of small pixels, small regions, I would say. Basically the size, the feature size is decided by the dimension of each of the cell, right? Each of the pixel cell. And as you all know, what is the length in x-axis and what is the length in y-axis, and also use this counts. Then you will tell what is the dimension. Let's see, this is x and this is y. Then you will tell what is the dimension of each of the small pixel in x and y. And that will be the 3D printed feature size, the minimum ones. All right, that's how you are able to compute it. Any question? Okay. So there could be some variations, as I mentioned. For example, you have known the dimension of the projecting image. Let's see, this you have known. Let's say 50 millimeter. All right, and this you have known. Let's see, 25 millimeter. All right, and you have the two angle as well. For example, you have known them. Then the question could be, well, you need to compute what is the distance from the camera to, I mean, from the lens, projector lens to the projection plane, right? Basically, it's a similar process, but in a reverse way. So that means you you have the same same computation, but plug the numbers at different places, right? That in this time, this distance is unknown, but all the rest are knowns, right? You should be able to compute it as well. So that could be one variation for this one. Or sometimes you know the dimension of the project image and the distance. Let's see, this 35, but you don't know what is these angles. These are unknowns. These are unknowns, right? Same thing, use the same process and find out what are the unknowns, right? By plugging in the known value. Okay, any questions so far? Okay, good. There will be similar questions in your homework, and you should be able to practice by solving the homework question. All right, then we have this kind of question. Basically, that's related to the laser exposure in the Ryzen, right? And the key is this equation. And that is the centric equation you want to use. Let me move it somewhere, maybe here. Yeah. And again, it depends on what kind of knowing information you will have. For example, there's one question to compute the width of secured line at the surface. So that is asking you to have the dimension of this, right? So it turns out it happens at the surface. That means the z numbers is 0 because this axis is y and this axis is z, and at the surface the z should be 0, right? Then what you could do is, well, substitute 0 here, and now you have what is the laser exposure, right? And then you will have this number. Okay. All right. Also, you have known this is the when this happens, I think there's several sentences describe it. So the energy exposure will be figured out if you're talking about looking at the surface of the Ryzen. So at this point, the energy exposure will be the critical exposure, which is EC, and this is known. So that means if you plug in Z equals to 0, the laser exposure will be the critical exposure, and that is known. All right, or given. Oh shoot. Let me erase it. Given. All right. And we also know if we also have this one by plugging 0 to this equation, right? And basically this should be EC in this case. Then the question is asking you what is the Y value, and you could use, and the only unknown here is the Y, right? Then you can do a little computation to have the Y. but the y is only this width. So what you want to have is 2 times the y at this point. And it turns out you will have the width of the cured line at the surface, which is this number. So I think the essential thing to solve this question is you have to know, well, at the surface, the energy exposure is this critical exposure. And this critical exposure is a known number. And that's how you solve this question. Any question? No? Okay, good. I will also post this together with the lecture notes 8. And you can take this as a reference when you solve the homework questions. Okay, I think we can move on and talk about another process, just a start. All right, that's the lecture 9. So let's talk about the selective laser sintering process. So what it looked like, let's check the video.
Selective laser sintering, or SLS, is a rapid prototyping technology that turns 3D CAD data into physical parts in a matter of hours. SLS is an additive manufacturing technology that uses powdered nylon 11, nylon 12, and PEEK materials. Parts produced are lightweight, highly durable, and both heat and chemical resistant, making SLS an excellent choice for producing production parts without the expense of tooling. The SLS process begins by splitting 3D CAD data into thin cross-sections or layers. The data is then transferred to the SLS additive manufacturing equipment. The machine then begins to create the first layer. After a leveling roller spreads a thin layer of powdered material across the powder bed, a CO2 laser traces the cross-section on the material. As the laser scans the surface, material is heated and fused together. Once a single layer is complete, the powder bed is lowered to make room for the next layer. More material is introduced from the powder cartridge and rolled out smooth, while unused material is recycled. The process is repeated, building layer upon layer until the part is complete. As SLS parts are built, they are encompassed by unsintered powder, which provides supplemental strength and eliminates the need for support structures. Complex designs and assemblies, once thought impossible, are now being redesigned with SLS as cost-effective integrated structures. Solid Concepts manufactures parts utilizing nylon with property-enhancing fillers to create rugged SLS parts suitable for a variety of prototype and production applications. Typical uses for SLS include tools and fixtures, fuel tanks, flight-rated components for unmanned aerial vehicles, automotive designs, air ducts, architectural models, and artistic sculptures.
All right, as you can see from the video, so basically the SLS process consists of several key points. So essentially it hardens the powder, plastic powder, through a selective laser energy. And there's a roller which will spread a thin layer of thermoplastic powder onto the newly built part. And then the platform will move downward and repeat this scanning, hardening, and spreading of material and lowering platform again and again until the part is built. So the different basically there's a unique point for this is since during the building of the model, the object, it is buried in the plastic powder throughout the whole process. So that means it does not require support material, right? Because the powder will support the uncentered part, uncentered powder will support the build part. So that's a unique point for this process, right? There's a new term which is sintering or melting. So actually they are different. Sintering basically will kind of provide some fusion between the material particles. But the melting is a better, I would say, will fuse the particle more such that it has a stronger bonding between the particles. It usually will generate higher density part than sintering, right? That's basically you should understand sintering will be little less diffused for the neighboring particles, but melting will have a more fusion between the particles. Right? So if you look at the process, selective laser sintering or selective laser melting, then you should know the difference between the two, right? That the difference between how you fuse the particle in between the neighboring ones, right? And there are different powder consolidation methods, right? There are solid state sintering, and basically there's no melting at all, right? And also there are liquid phase ones, and basically the two components, one melt, the other doesn't, or partially melts. So the full bulk of particle do not melt, just the skin will melt. Or they are full melting. So that will create the higher density close to a full density process. So if you fuse the particle more and more, that requires more energy, higher temperature, more strict processing conditions, right? So it depends on the material and also the function you want the part to serve. And so you could choose different ways for the melting or the sintering. Since it's also a laser-based process, so it has similar parameters. First is the laser power and also a spot size, scanning speed, which is quite similar to the stereolithography, right? And there is a hash spacing. So basically it represents the spacing between different scanned tracks, right? And laser thickness. Also, during the process, the powder bed will be heated up to certain temperature. So there's a powder bed temperature. Usually the entire chamber of the machine will be heated up to about 10 degrees Celsius below the melting point of the powder. And the reason is that could increase the laser scan speed. Basically, if the powder is lower, the powder temperature is much lower than the melting point, it will consume more energy to be melted. In that case, the laser has to be very slow in order to melt the powder. So by heating up the chamber, that increases this scanning time, scanning speed. Another benefit is from the material property perspective. And because the temperature difference is small, the built part will have less residual stress. So in order to reduce such a residual stress, it is desired to heat up the whole part to certain temperature, which is 10 degrees Celsius below the melting point. Also, another requirement is the a nitrogen atmosphere that is will be filled in the chamber. The reason is without such a nitrogen atmosphere, there could be some oxidation during this process for the nylon powder used in the process. So in order to reduce such oxidation, basically that requires the nitrogen atmosphere be filled. Then speaking of the materials, we'll also use thermoplastic in the stereolithography, and a polyimide, which in short nylon, actually is the most widely used one in the selective laser sintering for polymer process. And those ones like SLA, which is the amorphous thermoplastic, are rarely used because I mean, in principle, this kind of material will have worse material property and mechanical property versus those polymers which can actually crystallize. So that's why the those crystalline thermoplastic material are used in such a selective laser sintering process. So again, the thermal process, we need to take a look at the temperature. And for the temperature, those semi-crystalline or crystalline thermoplastics, it has a glass transition temperature, right? Which is usually around or below the room temperature. There will be a distinct melting point and a subsequent flowing of material. Or also there will be a significant change in volume above the melting temperature. But for the amorphous thermoplastics, no clear melting points. And the glass transition temperature is around 100 degrees. Also, that will gradually soften to another level that the material will begin to flow. So that is undesired for the printing process. Basically, you have no clear melting points. That's hard to plan your process and build up other parameters around it. So that's another fundamental reason why the crystalline or semi-crystalline thermoplastic are more desired in the process. So we have some equipment to measure the thermal energy, like the differential scanning, calorimetry. This is tongue twister. Calorimetry, okay, something like that. DSC, right? DSC equipment that measures the amount of heat needed to raise the temperature of the material to a certain amount of a certain amount of material to a certain temperature. And by doing so, you will have a clear understanding of the temperature and also the related thermal energy required, like the curve showing here at each of the points. I mean, the critical temperature, like the melting point and the gas transition temperature, how many heat energy are required, something like that. So in this process, the ideal polymer should have a narrow melting range. So it can go from no powder melting to complete melting with just within just a small increase in the temperature. That will make this process easier to control, right? You can just heat up a small amount of heat up the material to raise the temperature in a small amount, and then you will complete this melting process. So that's why we are preferring PA12 than the PA6 nylon material. The reason is, again, looking at this range, right? The melting range. This one is smaller. I mean, the upper one is smaller. This one is smaller compared to this one, right? In this case. Another phenomenon during the process is the crystallization. And so basically, the rate of polymer crystallization is at a minimum near the melting temperature and at a maximum in between of the glass transition temperature and melting temperature. So that is related to the solidification process. So basically we need to have a uniform crystallization and have a uniform shrinkage in order to minimize the part distortion. And also we want to avoid the melting point window and the glass transition point window to be overlapped, and that will have a significant sorry, that will have some issues for the lower layers during the building, and that's not desired for the process. So again, you have to select the material carefully to avoid such a overlap. Oh, it's not a glass transition window, it's the cooling temperature. Another one is the melt velocity. After the material is heated up, it becomes a liquid state, and the velocity of the polymer should be low enough to flow out to a full density before the temperature fall below the melting point. So that is related to the material itself, and low melting velocity tends to produce a high shrinkage, and essentially it will cause a low part accuracy. So there is a way to determine the melting flow velocity if we conduct such a test. Basically, this is the melt flow index testing, and that is measured using the ASTM D1259. As you can see here, we have the pellet of the plastic, and it will be heated up in this device, and then it will measure the molten plastic flows by setting up certain temperature. See, that's how it works. So as you can see here, at the bottom, it flows through a small holes, and all the parameters will be recorded accordingly. And so basically, the polymer chain length will increase with the time at a elevated temperature, and that will cause the different melting flow velocity. So if another interesting property you want to look at is the powder reuse and recycling, right? As you saw in the video, there's only a portion of plastic powder used, I mean, solidified during the process, and all the rest are still in the powder form. So you cannot just dump all the remaining powders. Instead, we should think of ways to reuse them. But the problem is after the because there will be a heat up of the whole of the powder and the environment, so the material property degrade, mechanical property degrades as well. So in order to at one hand reuse those powders, and on the other hand remain a high quality of the printed parts, we mix the different powders. One third of new powder, 1/3 powder from the overflow bins, and 1/3 used powder from the build chamber. So you might ask, what is the overflow bin? Let's go back to a figure maybe. Here. See, so basically, when the roller spread material, there could be some excess powder fall down from the platform. So there will be a bin over here. I think both of the two sides, and for this kind of remaining powder. And this is different from the powder still inside on the platform. So 1/3 of this, 1/3 of new one, and 1/3 from here. All right, that's the 3 portion of the powder. And some of the manufacturers of the printers, 3D Systems, EOS, Proudways, Formlabs, and Centerit. We have a Centerit select laser centering machine in the lab, but for a long time we haven't operated on it because it's not good to use. I mean, it's very difficult to use, and on the other hand, the powder, right? You don't want to get exposed in a powder environment. So we just let it be and let it sit there instead of utilizing it. But there are big ones in the Imprint Center, which is in use. So let's look at the design principles for such a process. And basically, this design guidelines or principles are related to certain process. And the first step, the first principle is the angles of the plane. So in order to avoid the step effect, the angle of the plane should be either 0 degrees or larger than 20 degrees to the XY area. And basically, if you look at this, that tells how you measure these angles. The visibility and the size of the step effect, stair effect, will also be related to the layer thickness, right? So that's how you determine what kind of feature you want to have on your part. So there are pins and holes for some of the parts. So there are some smallest holes or pins that could be printed using such a process. And that basically, these numbers are very important, right? What is the smallest for the gaps in between of the X and the Y direction, and that will constrain the feature or the size of pin and holes. And also some of the variables, gap between the bush and the bots, length of hinge, diameter of the bot, wall thickness of a surrounding bushing, and build directions. This will affect your decision as well, according to the different geometry. There's no, I would say, a unified guidelines. You have to have a little trial and error to learn from the experiences. For example, if you look at the feet, right, there is different feet. If you are talking about some loose connections, 0.1 millimeter difference between the pin and the holes would be a good practice. Also, if you're talking about some tight fits, definitely this distance will be reduced according to how tight you want this assembly fit to be, right? Here shows the fonts. Basically, these are the letters could be added onto all the words can be added onto the prints. And there are different fonts for different printers. Some of the minimum feature size, the wall thickness in X and Y and Z. As you can see here, in the XY minimal wall thickness is 0.45 to 0.7 millimeter. And in this direction, the wall thickness for one layer is 0.0 or 0.15, depends on the machine. Depends on the different system you're using. For the pins, minimum pin diameter 0.8 millimeter, and also but usually this is an ideal case. In order to increase the repeatability, a 1.8 millimeter would be a better practice. So you can see if you decrease or increase the gap width, what will it look like for the prints, right? Same thing happens if you are decreasing the hole diameters, and it turns out there will be some failure starting from like I would say 0.8 millimeter, right? Sorry. So the build speed is depending on the Z height and also the overall volume of the parts. Sometimes you want to design it in the way that you could have a better integration of the different parts, a lightweight, and also some design with a load bearing or some other functions like the heat bearing also. Since we're using powder, and powder will fill the space during the process. So if you're printing something like this spiral pipe, and then you need to think about if you could remove the remaining powder after build. And if you do not have a opening, then that means it's really hard to build the powder, to remove the powder during the printing process. Actually, that is similar problem for the stereolithography process. In the stereolithography, if you do not be aware, if you're not aware of your design, there could be cases the liquid material is trapped in a volume. That happens if you do not have an opening. That is the exact same case as what we have for the powder-based ones. If we do not have opening to let the powder go out, there could be some powder remaining in your part, in those internal space of your part. All right. I think that's all for today's lecture, and I will post the lecture notes together with the questions of homework 3. So any questions so far before we end the class? No? Okay. Let's keep in touch and see you guys.
Professor,
Yeah.
I did have a question. Can you, okay, you can hear me. So you'll post the groups on my courses, right?
Yeah, I will post it. Yeah.
Because I don't know what group I'm a part of yet, and I I know a few people, so that's why I'm seeing like if there are some stragglers that I could either join. And
Oh, did you talk to anyone about the groups?
the day people were picking groups, I was sick, so I didn't want to.
Oh, okay. Yeah. I mean, you can definitely, yeah, with the information, you could decide if you want to join some of the group and also start to talk with them.
Yeah, of course. Yeah. Thank
Okay,
you.
good. Yeah, I will do that.
Yeah, thanks.
Professor, I emailed you my group requests at the beginning of class. If that doesn't work, that's fine. I can just get put in a random.
Okay.
I don't know if somebody else already emailed you our list, so.
Yeah, I will look at it and make sure you will have a group as you want. All right.
All right, thank you.
No problem.